In this video, we're going to talk about inequalities again, but this time with polynomial and rational functions involved. Okay, so there's two main ways that you can solve these. So the first is using a graph. So if we have the graph of the function, then the solution to f of x is bigger than 0 is the open intervals where the graph is above the x-axis, right? Because these f of x represents the y values, right? So we want here the y values to be bigger than 0. So that means we need the y's to be above the x-axis. Okay, similarly, if you have the inequality where you're less than 0, then you want all the y values that are below the x-axis. Okay, and it works the same way for the inequalities that include equality, but then we're going to use a square bracket for the x-intercept if it happens. So let's see an example where we have the graph. So here we have this graph. It's a polynomial. It's an even polynomial because of the end behavior. Goes both up. So if we were looking for where is f of x less than 0, okay, so that means we want the function below the x-axis. Okay, so let's just point out these points. So where the x-intercept is, this is -3, 0. This one is 1, 0. And this one is 4, 0. Okay, so now where we're below, okay, is this interval here. Now at 1 we're equal to, so we're not strictly below. And then in this interval here. So that means our solution in interval notation is going to be -3 to 1. Okay, but I can't include 1 because of the strict inequality here. And then from 1 until 4. Okay, not including any of the endpoints. Okay, now if we wanted where the function is bigger than or equal to 0, now we do want to include the endpoints. Okay, so let's highlight this one. So where we're bigger than 0, so obviously bigger than or equal to, so obviously all three of these x-intercepts are where we're equal, and then bigger means that we're above the x-axis. So that's going to be those intervals there. So what we're going to write is -∞ to -3, including -3. Okay, and also the x value 1 all by itself, because it equals 0 there. And then also including 4 all the way to infinity. Okay, so that would be our solution in interval notation for that one. Okay, so if you have the graph, it's easy to tell when you're comparing to 0. Okay, so it's easy to see if you know the x-intercepts, you know where it crosses or doesn't cross the x-axis. So then you can find where it's above and where it's below the x-axis. So maybe I should just write here above or touching, okay, x-axis. Okay, let's try. I'm going to leave number 2 for you to do, but let's try number 3 here. So when we're looking at a rational function, we want all the places where, because we want to compare this function to 0. We want all the places where it could switch from positive to negative or negative to positive. Okay, these are definitely the x-intercepts, but they're also the vertical asymptotes, if there are any. Because on a vertical asymptote, so let's say I had one here, the graph could do that, right? So then it could switch from positive to negative. So we want to find all the, so let me just write here. So the first thing we want to do is find the x-intercepts and the vertical asymptotes. Okay, and we want to sketch here, so we kind of want those things anyway, because we're using the method 1, which is the graph. Okay, so for this one, the domain, so it's in simplified form, so I can't have the bottom equaling 0. So I can't have x equals 1 or x equals negative 2. Now both of these are vertical asymptotes. So because we're doing the sketch, we might as well sketch them in. Okay, so there's the asymptote x equals 1. And then we also have x equals minus 2. Okay, now we want the x-intercepts. So we want to solve f of x equals to 0. So when is the y value 0? So we have 0 is equal to x over x minus 1, x plus 2. Now this only happens, it's 0 exactly when the top is 0. So that's when x equals 0. So we get a point at 0, 0. Okay, so we're going to have a point there. Okay, now those are the places where it can cross. Now we're using the sketch. So at this point, I guess we want to see if there's a horizontal asymptote. Now the degree of the top is 1, and the degree of the bottom, so there's x's times x's, it's going to be 2. So the degree of the top is smaller, so that means that we do have a horizontal asymptote at y equals 0. And obviously we've already found where the graph crosses that asymptote because those are the x-intercepts. Okay, which there happens to be one of. Okay, so now we make our table. So we want to put in, we want to put in all of the places where the top and the bottom are 0. Okay, so the first one on the number line would be at negative 2. Okay, and then it's at 0. And then it's at 1. Okay, so 0 is where the top is 0. And 1 and negative 2 are where the bottom is 0. Okay, now I want to check something in between, so let's do maybe negative 3. So f of negative 3 is going to be negative 3 over negative 3 minus 1 is negative 4, and negative 3 plus 2 is negative 1. So this is going to be negative 3 over positive 4. Okay, so we get a point at negative 3 over 4, and in this interval we're below the x-axis. So negative 3 is here, and negative 3/4 is around there. Okay, so now let's try, say, negative 1. So that's going to be negative 1 over negative 2 times 1. So this is negative 1 over negative 2, so positive 1/2. Okay, so in this interval we are above the x-axis. So negative 1, we're at positive 1/2. So then we have to try something between 0 and 1, so maybe 1/2. So that's going to be 1/2 over 1/2 minus 1 is negative 1/2. And 1/2 plus 2 is 5 over 2, so it's 2.5. So if you simplify that, I think you get negative 2/5. So we get the point at 1/2 and negative 2 over 5. So I think that's about negative 0.4. Okay, so we're going to be somewhere down there. And then lastly, something bigger than 1, maybe we do 2. F of 2 is going to be 2 over 1 times 4. So that's 2 over 4, which is 1/2. So we get the point at 2 and 1/2. So at 2, we're at 1/2 here. Okay, now we can sketch the graph like we did in the last section. We're in this interval here where x is less than -2. We know that the function's always negative, which means that we're going to have to approach the vertical asymptote towards -infinity, and then we approach the horizontal asymptote below it. So it's going to look something like that. In the interval from -2 to 0, we're always above. So we're going to go like this. Okay, and in the interval from 0 to 1, we're always below. So we have to look something like that. Okay, and in the interval when I'm bigger than 1, it's always positive. So we have to approach the asymptote to the positive infinity and the horizontal asymptote above. Okay, so that's what our graph looks like. And I didn't leave myself a lot of room to actually answer the question. So let's try and fit it in here. Maybe I'll just erase these. Okay, so f of x is less than or equal to 0 on the interval. Okay, so I look on the graph. Maybe let's highlight. So less than or equal to 0. So I want below the x-axis. Okay, so that's this part, the x-intercept, okay, and this part, and that's it. Okay, so that's going to be from -infinity to -2, obviously not including -2 because there's a vertical asymptote there. And then from 0, but we include 0, to 1. So that's where the function from the graph is less than 0, less than or equal to 0. Maybe I'll do a line down here as well. Okay, so another method that we can do, so we didn't really need the graph there. In fact, I had already started writing above and below on my table. So we can actually solve it using that. So that we call this algebraically. So because the polynomial and rational functions are continuous on their domain, it means what I've been saying all along, so they only switch from positive to negative or vice versa when they cross the x-axis or when the function's undefined, so a vertical asymptote. Okay, so these ones are x-intercepts. Okay, and these ones are vertical asymptotes. So that's what we've already been putting on our number line, on our table. Okay, those are the only places where they can switch signs. So that's all we need to check. So what we want to do, always compare to 0. Okay, so rearrange the inequality so you have 0 on one side. Solve for where the numerator is 0. So if it's simplified, okay, these are the x-intercepts. Solve for where the denominator is 0. Okay, these are where the vertical asymptotes are. Plot the solutions on a number line. Okay, now like we do when we're graphing, on each interval in the number line, test a value. Okay, what you want to see is if it's positive or negative. We don't actually care about the value. Okay, so only care if it's positive or negative. Okay, we don't actually really care about what the value is. And then we can answer the inequality. So let's do number 4 here. Okay, so first of all, we want to compare to 0. So I'm going to move the 9x over, 9x squared, sorry. So I have x to the 4 minus 9x squared is less than or equal to 0. Okay, now I'm going to, so this is not a rational function, it's just a polynomial function, which means it's continuous everywhere. So I just want to find the x-intercept, so I'm going to factor, so I can take out an x squared, and that's going to leave me with x squared minus 9. Okay, so x squared times x squared minus 9 is equal to 0. So I just want to find the x-intercepts. So I'm going to factor, so that's a difference of squares. So it's x squared times x minus 3 times x plus 3. Okay, so, oh, not the inequality, sorry, equals. So that's going to happen when x equals 0, x equals 3, or x equals minus 3. Okay, and this thing, x squared times x squared minus 9 is never undefined. Okay, so we don't have to worry about that. So we make our little table. Okay, so we put on, so negative 3 is the smallest one. Okay, and then I have 0, and then 3. And I want to test a value in each interval. So maybe I test negative 4. Okay, so if I plug in, I'm going to plug into here, although you could plug in anywhere. Okay, so that's negative 4 squared. Negative 4 minus 3 is negative 7, and negative 4 plus 3 is negative 1. So now I don't care what the number is. You can compute this number if you want. But to be a little bit faster, once you get better at it, okay, this is going to be a negative number squared times a negative number times a negative number. So a negative number squared is actually a positive number. Okay, and then when I have two negatives, I am going to get a positive. Okay, so on this interval, it's positive. So that means it's above, well, it's above the x-axis. Okay, actually, I'm going to write positive instead. Okay, now I'm going to check something between negative 3 and 0, so maybe negative 1. Okay, so that's negative 1 squared. Negative 1 minus 3 is negative 4. Negative 1 plus 3 is 2. So again, this thing's going to be a positive because of the square. This one's a negative, and this one's a positive. So I'm multiplying two positives and a negative. That's going to give me a negative. Okay, so it's going to be negative in that interval. If I do 1, then I'm going to have 1 squared. 1 minus 3 is negative 2, and 1 plus 3 is 4. So again, positive, negative, positive. So this interval is also negative. Okay, now if I try 4, that's going to be 4 squared. 4 minus 3 is 1, and 4 plus 3 is 7. So here I have a positive, times a positive, times a positive. This is definitely positive. Okay, so x to the 4 minus 9x squared is less than or equal to 0 on the interval. So remember that these places are all equal to 0. Okay, so this one is 0, this is 0, and this is where it equals 0. Okay, so they're not undefined, they're equal to 0. So they're going to be included in the interval. So we actually could just say on the interval from negative 3 to 3, including the endpoints. Okay, we don't have to split at 0 because it's negative on both sides and equals 0 at 0. So that would be our answer here. Okay, now I'm going to leave number 5. Actually, I'm going to leave the rest for you to do. So number 5 here. Now remember for 5 and 6 actually, that you want to compare to 0. Okay, so that means that you're going to want to move the 1 over And then you're going to want to simplify that into one fraction so that you have a new rational function. Okay, that's going to make it easier. So same over here. Okay, so compare to 0. Okay, so move one thing over and then combine the two fractions into one fraction. Okay, that's going to help you solve those. And that one I think you can do as well. So I'm going to leave the rest for you to try. I'll make a new video with them filled in case you have any trouble. But it would be very good practice for you to try those ones.